Good afternoon. Okay, if you have any preliminary questions, you can ask them now. Otherwise, we just go directly to what we were starting to do last time. Okay. So the goal is to describe wave packets. Okay. And we decided to look at an object like this, psi of x being an integral in dk, where k is a one-dimensional variable, e to the I kx. So k is the wave vector of this plane wave. Okay, this is cosine kx plus I sine x. So you superimpose, you sum infinitely many plane waves. Obviously, you have to decide how, and you do it with this g of k, okay? The weight function. And for reasons, okay, which will be clear in a while, you put also square root of 2 pi there, okay? So this is, strictly speaking, just a Fourier transform of g of k into psi of x. But seen physically, it's a superposition of plane waves with some weight. In order to proceed with the calculation, we will make a choice for this g of k, and we will select it to be a Gaussian, okay? So some normalization constant, more about this later, times e to the minus alpha, some constant, k minus k0 square. Okay, so it's a Gaussian centered around some wave vector k0 with a certain width of the Gaussian that depends on alpha. Okay, in fact, it's inversely proportional to alpha. And we have to learn how to calculate this. Okay, so let me. The other thing is that I will choose C in order to normalize everything, and the way we insist in normalizing things is the following. For instance, g of k is normalized in such a way that its square modulus integrated over dk is 1. Okay? The reason why we insist on normalizing things with the square also will be clear in a while. It's essentially related to the fact that it's not psi that determines the probability that psi modulus square. So that is what is needed to be integrated over x, for instance, in this case, and be 1. And similarly in spirit, g of k also needs to be square. But this is just a technicality, and is also a matter of convenience in some sense, because everything is linear. If I multiply by some other c, well, psi gets multiplied by a different factor, but doesn't matter much, okay? So let us start learning how to calculate these integrals. And for that, I will appeal to something that you probably know, which is the following. If you have this integral over dk of square root of 2 pi e to the minus k square over twice some constant, let me call it sigma k square, okay? How much is this? Okay? Almost 1, almost 1. I mean, if I write it like this, okay, e to the minus y square over 2, then this is 1. Really, okay? But here you see I have k divided by sigma k square. So if you want, I should here put 1 over sigma k, and after I do that, I exactly have that integral. Okay, so this is 1. You should learn to argue also on the dimensions of things, okay? So if here k is a dimensionful object, k here, what dimension does it have? 1 over length, because it multiplies a length, and the result is just a number. Okay? So in the same spirit, this sigma k is the same dimension as k. And you see that this is dimensionless. But here there is a dk, which is same dimension as k. Okay? And in order for this object to be dimensionless, you have to divide by sigma k. Okay? So the result should be of the same dimension as k, so sigma k here. Okay? Very good. Now, another way of writing it that you sometimes find is the following. Integral in dk square root of 2 pi e to the minus a k square over 2. Sometimes you find it this way, just a constant a in front, rather than having 1 over sigma k squared there. Well, the result is obviously copied from that, and you simply have a equal to 1 over sigma squared. Therefore, here the result is 1 over square root of a. Nothing but the same integral. Now, is this the only integral that we can do? No, we can, in fact, play considerably on this couple of formulas to learn, for instance, the following. Suppose that I want to do now this integral in dk over square root of 2 pi e to the minus a over 2 k square plus k times some variable, okay, which I call it j. You shouldn't think of it as an integer. It's just some real number, j. Okay? So you see this is now a Gaussian with an extra linear term. But certainly, as far as convergency is concerned, this is not a problem, because for a very large case, this wins. Okay? So in any case, this thing is going to 0. And the integral, therefore, exists. But whenever you see a k square and a k, you start thinking of completing a square, right? And I would like you to consider this to be just k. Let's see, you need some j here, and you need the square. Let's see. Well, if you put here a minus j over a, the mixed product is what? It's, you see, minus 2k j over a, which multiplied by this minus a over 2 becomes kj. All right, okay? So what I want. Fantastic. So the k square is the same. The kj comes from there, but there is an extra piece, okay? The extra piece that you get from here is e to the minus a over 2 j square over a square, or if you want, j square over 2a. All right? Well, every time you insert something, you should just remove it. And therefore, here I have to multiply by j square over 2a. Okay? So this thing here, let me erase the unnecessary things, you can verify is identical to this. Okay? The k square, the kj, and the j square from here is cancelled by that. All right? Okay, now, this object, therefore, this integral is equal to e to the j square over 2a times the integral in dk over square root of 2 pi of e to the minus a over 2. Now, not k, but k minus j over a square. Now, is this integral fundamentally different from this? No, because you can change variable from k to k minus j over a, just a shift. then dk is just the same, exactly the same variable. And the limits also, I never indicate them. They are always from minus infinity to plus infinity, and obviously a shift doesn't matter. Okay? Good. So this integral is exactly the same as this. So 1 over square root of a. Result, this is e j squared over 2a divided by square root of a. Okay? So if you allow me, I now take this formula, I put the plus kj there, and here I insert j squared over 2a. Okay? Obviously, this generalized the previous one. If you take j equals 0, you recover the previous one. Okay? Good. One step more. But now, until now, everything is real. Okay? So k is a real variable, j is a real constant, and we are happy. Real functions, which can be integrated in this way. But what about if j, instead of being a real quantity, is just purely imaginary, for instance? Suppose that j is equal to I times x. Well, first of all, this suggests why I'm doing that. Because I have here e to the I kx, and here I have, in fact, a Gaussian with some k square piece. So you start understanding where I'm going, where I'm aiming at. Okay? Well, if j is imaginary, this thing here is e to the I kx. Obviously, there is an imaginary part, a real part. The real part is cosine kx. The imaginary part is sine kx. And therefore, you have really two integrals. But formally, nothing prevents you from doing them. Okay? And in fact, strictly speaking, the result I have derived doesn't use, I mean, in a fundamental way, the fact that the integral was of a real function. I mean, the thing is pretty much general, and if j is equal to ix, you can just read from the very same formula the following. Integral in dk, square root of 2 pi, e to the minus a k squared over 2, e to the I kx equal to e to the, now, j is now I times x. When you square, you get minus x squared over 2a. Then you have the usual square root of a. Okay? Now, this is something that I would like you to notice. It tells, in words, the Fourier transform, this is a Fourier transform, of a Gaussian in K space, okay, is a Gaussian in X. However, one should notice the following thing. Here there is a factor 2 and the factor 2 the same. But here there is an a in the numerator, and there the a appears in the denominator. Okay? So the width of those Gaussian is reciprocal. Okay? Something that is wide in K space is narrow in X space, and vice versa. Something narrow in K space is wide in X space. Okay? Because you know that if you exchange this, I mean, if A is small, 1 over A is large, and vice versa. Okay? So this is a nice formula. It's about Fourier transforms of Gaussians that are still Gaussian, but with a reciprocal width. And please try to, well, remember that you know at least. I don't pretend that you remember every single detail, but at least you should remember that you know it. And if necessary, indeed, you can reconstruct it with this couple of steps from the original integral equal to 1. Okay. There is no quantum mechanics in principle here. This is Fourier transform. Okay, this is waves. However, you will soon notice that this is, in essence, a statement about Heisenberg uncertainty principle. Okay, uncertainty in K and uncertainty in X, so in momentum and in position, are reciprocal to each other, and their product is bound from below. Okay. Now, this is, I think, all we need to proceed. Okay. So this is all the mathematics that we will use in the next half an hour or so. By the way, with this thing, you should, for instance, be able to calculate what is C here. Okay? Just to show you what is the type of calculation that you would need. Here you have that 1 should be equal to the integral of what? C squared e to the minus 2 alpha k minus k0 squared. Okay? Well, first of all, again, shifts of k doesn't matter. Okay? So this is the same thing as the integral of k squared. Good. Next, well, next you can use, for instance, well, whatever. The first. Only you have to be careful. This thing here, you better call it, for instance, 1 over 2 sigma k squared. And then you have exactly the first formula, okay? So the first formula would tell you that this is equal to c squared times, there is a square root of 2 that you have there and not here. So you just put it, and then the result is sigma k, okay? So for me, sigma k is related to alpha in this following way. Or if you want, sigma k squared is equal to 1 over 4 alpha. Okay? Well, then you can solve for C, for instance. Okay? And if you solve for C, you will determine the fact that C, the normalization constant, is 2 alpha over pi to the power 1/4. Okay? Very simple algebra. Okay, this is just a side discussion. Okay, so it shows you how to use that formula to calculate the normalization in front. Before I proceed, so let me just put the result here. So C is equal to 2 alpha over pi to the power 1/4. I leave this there, okay, for a reason. This way of writing Gaussian is particularly nice because sigma k has a very nice physical meaning. Okay, sigma k is the width of the Gaussian, okay, and also gives you the second moment. If you have a probability distribution, okay, in this case, let me call it P of k, you know that you can calculate moments of the probability distribution, okay? The first moment is usually called the average, okay? And is just a multiplication of the probability times k, okay? You always assume that these things are normalized to 1, as any probability should be. This is the first moment, k average, the average. The second moment is called usually sigma square and is integral of k minus the average k square. Okay? You have seen this, okay? This is classical probability. So it's essentially, it tells you how width is, how wide is the distribution around the mean value, okay? So if this P of k is something centered around some point, okay, some average k, it tells you something about the spread, the variance, how it's going, okay? Well, it's very simple to show that indeed this sigma square defined in this way is exactly, if you take this probability distribution now, so this is the P of k, okay? It's a Gaussian, normalized in this way so that the integral is 1, okay? So this is verified. So this for me is the P of k. Let's calculate the average here. The average is how much? 0. No, average, not the average square, just the average. 0, because this is centered in 0. I should redo here the plot. If this is k, and this is P of k, it is centered in 0, okay? It's something like this. So the average is just 0, okay? Good. Notice, if I do this shift, things change. Huh? If you calculate the average for this distribution, you will find, no surprise, k 0, okay? Not 0, okay? But let's proceed with that because it's simple. So this is just 0 in that case. So this disappears. Let us calculate now the integral of k squared times P of k, which is that object there. So square root of 2 pi sigma k e to the minus k squared over 2 sigma k squared. Now, in order to calculate it, the best thing is if you divide by a sigma k square and you multiply by sigma k square. Okay? Now you see that the variable k over sigma k, you can call it y, is always appearing everywhere. Okay? So this thing is equal to sigma k square integral in dy square root of 2 pi y square e to the minus y square over 2. And it doesn't take long to deduce that this integral is exactly equal to 1. Okay? In case you want a proof of that, one possibility is the following. Take this formula, okay? Put j equal to 0, so the previous version without this, okay? Take a derivative of both sides with respect to a. If you take the derivative of this side, you bring down k squared in front with the minus and the 1/2, okay? And it's exactly the integral you want, essentially, integral of k squared. The derivative of that side brings, again, a 1/2 and a to the minus 3/2. Then put a equal to 1, because you want, after all, here 1, and you will discover that the whole integral is just 1. Okay? Very simple derivation. Just please try to do it, because it makes you confident that you know how to do things. Okay? So the result is that this integral here is just equal to sigma k squared. Okay? So the width defined in this standard way, second moment, is just sigma k squared. The parameter appearing there. Okay? This is no surprise, you know, okay, that the physics of the Gaussian width when you write sigma in the denominator in this way is exactly this, the variance, the second moment. Okay? This is slightly more physical than writing it this way. Okay? Because you have always to remember that alpha is not the width, but is the inverse of the square of the width, with some factors 2 also. Okay? So it's better to, in some sense, to make reference to this if you want to discuss about widths rather than to just some alpha there. Okay? But you can translate from one to the other in this way. Okay, is this clear? Good. That's the end of general mathematics, say, or simple integrals. Now let us approach our calculation. Okay. let me write here. This I write for you here. Sigma k square is, so the width of the square of this thing is just 1 over 4 alpha. Okay, so let us calculate now the integral, okay? Psi of x is equal to the integral over dk square root of 2 pi. I will do at least this very first calculation in all details, okay? Later on, probably I will skip some steps, but I encourage you, when you do the calculation yourself, to always be very, not skipping too many steps, because it's very difficult if you have done a mistake in the skipping to just notice the mistake, because it's in the air and not on the page, okay? So please write everything in an orderly fashion, okay? Straight lines. I always see in the homeworks and in the exams, especially if you are in a hurry, lines that start flying around, the diagonal things, things that mix. Just be ordered, okay? Being very careful in the writing and in the order of your equation is an ingredient, you would be surprised, for success, okay? Getting the right answer. Okay. And it's also very easy to go again over the calculation and correct the things if something is wrong. If everything is messy, the first equation is here, the second comes there, the third comes wherever in the page, you will never find it, okay? And obviously it's a nightmare for whoever has to grade and check, okay? So let's see. This is there. G of k is c, okay, which, by the way, we know. Then I have e to the minus alpha k minus k0 square. And then I have e to the I kx. Okay? Then I want to use that formula there. So before I do that, obviously, I have to get rid of this. Now, allow me, the power of the blackboard, to rewrite the k as follows. I have inserted and deleted, okay, so added and subtracted k0. So obviously, this object here is just e to the I k minus k0 x times e to the I k0x. But notice, we are integrating over k, not k0. So this is just a constant piece, which I can take out, okay? If I do that, I have c e to the I k0x, this one, times integral over dk, square root of 2 pi, e to the minus alpha, k minus k0 squared, e to the I k minus k0 x. Okay? Clear? Now, these are integral over minus infinity to plus infinity, and the usual trick, if you change variable to call it k prime equal to k minus k0, okay, then dk and dk prime are identical. The limits are unchanged by this shift, and therefore this, now I would be tempted, if you allow me, to just substitute here k. Well, maybe I shouldn't do it. I promised that I will do all the steps in the first thing. Okay, so this is equal to c e to the I k0x integral in dk prime, okay, e to the minus alpha k prime square e to the I k prime x. Okay? Now, if you allow me, I get rid of the prime. Okay? Good. Now we are closer now to that form. And in fact, we can copy essentially now the result. Only careful, here I have a over 2. Okay? And here I have alpha. But this is not a big problem. So let me just copy the result, and wherever I see there a, I should interpret, so the identification is alpha stands wherever A over 2 appears there, okay? So if you want, wherever I see A, I should just put 2 alpha. Okay? So let's do it. And I will do it here again. So this is equal to C, e to the I k0x. Okay? And what? E to the minus x squared over 2a. But 2a is 4 alpha. And in the denominator, I have square root of a, which is square root of 2 alpha. Okay? This is the full calculation, exact, no approximation, of the Fourier transform of this Gaussian centered in K0. Let me just do a little bit more, just to end this thing. And let me write it in the following way. If everything is clear, I erase here. Okay. I rewrite this as 2 alpha over pi to the power 1/4 divided by 2 alpha to the power 1/2. So you see that these 2 alpha really are related to each other, and you can just cancel the 2 alpha in the numerator, and this becomes 1/4 as well. Okay? So just put everything here as 2 alpha pi to the power 1/4. Okay? And e to the I k0x e to the minus x squared over 4 alpha. Okay? Good. Now, apart from this constant, let's examine the result. It is like a plane wave, okay? The plane wave with a wave vector which is k0, the one on which the weight is centered. Okay, remember, this is centered on k0, not on 0. Okay, so first approximation is just a plane wave. So if I draw it, say that I draw the real part, obviously it's complex. Let's suppose that you draw the real part, would be a cosine of k0x, something like this. Okay? Oscillating forever, obviously. Okay? This is x, and this is psi of x, apart from normalization and everything. Just this piece. This quantity here, obviously, is related to k0. It's the lambda 0. And you know that lambda 0 is 2 pi over k0. Okay. What about this factor? Well, this factor, obviously, makes, this is x equals 0. The factor is 1 there. But as you go away, depending on how much is alpha, this Gaussian piece will essentially make all the other oscillations to be smaller and smaller, okay? So if I were to draw this, okay, depending on alpha, it would be something like this, and then here maybe smaller, here is even smaller, here is even smaller. Okay, I don't know, I mean, okay? Something like this. Symmetric. Okay? Very, very small as you go away. So you see that the thing oscillates but also vanishes as you move away, which is what we want to describe. Okay? It's a wave, but it's also a packet, something that is essentially localized in a certain region of space, depending on alpha. I draw a kind of extreme case where alpha is such that, well, essentially you see only the central part. But if alpha is very large, if alpha is very large, then notice the width of this Gaussian is directly related to alpha. You could write this as e to the minus, well, I should make let me first look at the psi modulus square. If I look at psi modulus square, okay, which is simple, in fact, this is the modulus square of this. The modulus of the e to the ikx is 1, okay? So this is 1 over 2 alpha pi to the power 1/2 times e to the minus x square over 2 alpha, okay? So immediately see alpha is the width in x space, okay, directly. It is what I call the width. And if you draw it, so it's not no longer this, but it's something that doesn't oscillate. If you draw it, it's a simple Gaussian, okay, where the width of the Gaussian is controlled by alpha, okay? So if this is sigma, is the square root of alpha. So large alpha means a large width, many oscillations before you see the decay. Small alpha means a small Gaussian, means very few oscillations, and then nothing. Okay? Is this clear? Okay. Notice one thing. For this Gaussian wave packet, the width in k space, okay, sigma k, is how much? Is 1 over 2 square root of alpha. The width in x space is square root of alpha. So sigma x is square root of alpha. The product of the two widths, how much is it? Sigma k times sigma x equal to 1/2. Okay? This is probably reminds you of Heisenberg uncertainty principle, which in more general terms tells you that the variance of the momentum square root times the square root of the variance of the position is bound to be greater than h bar over 2. The 2 is the same. What is missing here is an h bar, and the h bar is due to the fact that here I'm looking at k and not at p. P and k have an h bar in between, okay? So this is essentially the lowest bound in Heisenberg uncertainty principle, okay? So those Gaussians that I have constructed realize the minimum uncertainty possible in Heisenberg uncertainty principle. Okay. Is everything clear until now? Okay. So this is like a photograph of our wave packet at a given time. As you see, time has made no appearance until now. The fixed time object. Okay. Now, let me consider time. Let me erase a few things. Should I keep this? Well, you have written. I will rewrite whenever I will need it. I need some space. Okay, and I keep this. Psi x. Okay. Now, let us start considering a single plane wave. The usual way you consider the time dependence of something like this is, for instance, by considering, again, a cosine and sine dependence on time, in this form, okay? Omega, in general, depends on k, okay? Let me indicate it by omega of k. Now, let's see what is the meaning of omega of k. Let me do the following. Let's put the k in front of everything. And then, obviously, here I have omega k divided by k t. Now, this is probably already suggested. You see, x minus something t. You would be tempted to call this v of k. Looks like a velocity. Dimensionally is a velocity, okay? So you call it v of k. It's called phase velocity. What does it mean? It means the following. If I have at a certain time, say t equals 0, this object at position x0, okay, at t equals 0, at what time and at what position I will have exactly the same value for this number, for this phase? At what time and at what x? Well, obviously, I want x minus vkt to be exactly equal to x0, okay? So t has increased, x has changed, but their difference in this way should be just x0. So the place x where I have exactly the same phase as the original one at time t, however, is just equal to x0 plus vkt, okay? So just to, if I have a certain function, okay, I take it at a certain place x0, the same value is moving, okay, with time at a phase velocity vk. You see, it looks like a simple motion in time, okay? Time equals 0 is this, and then it moves. All right? This is clear. Okay, let us insist. I still don't know what omega of k behaves in k, and therefore I don't know v of k as a function of k. Let us assume that there is such a thing. Okay, now I pretend to calculate the same thing now, but with time. Okay? Same calculation in spirit, but with time now present there. How do we do? Well, let's observe a few things. If this phase velocity is the same for every k, so essentially if v of k is just a constant, let me call it c, for a reason that will be clear in a second, doesn't depend on k, then I can do exactly this transformation there. Okay, so I have e to the I k x minus ct, okay, because the phase velocity is constant in k. And therefore, you see that the integral in k is identical to what I have done before. Okay, exactly the same calculation, except that now, wherever I had x, I should put x minus ct. Okay? So immediately conclude that whenever the phase velocity doesn't depend on k, but is just a constant, the wave at position x and at time t is exactly equal to the same wave at time t equals 0, but at position x minus ct. Okay? Is this clear? It's telling you simply that as time advances, the wave simply moves, shifts rigidly, okay, with the common velocity c. Whenever this happens, you say that the wave does not disperse. So this is a non-dispersive wave. Okay? So whatever signal you have, a complicated wave, if every phase velocity is identical, then the signal simply shifts and moves rigidly. Okay? Non-dispersive wave. Now, this happens for electromagnetic waves in vacuum. Okay? Every phase velocity is the same. It's the velocity of light. Okay? And the wave moves as a whole with the velocity of light. Okay? Notice electromagnetic waves in vacuum. If you are in a material, that's no longer true in general. Materials are called also dispersive media, in the sense that the index of refraction depends on k in general, and therefore the velocity of each single k value is different in general from k to k. And you do no longer have just a uniform shift. The wave has a tendency to disperse, to broaden, to, okay? So not only a rigid movement, but some broadening and things like this, okay? Which is characteristic of dispersive media. So whenever C of k is different from just a constant, V of k. Okay? By the way, if you reread in terms of omega of k, this case simply means omega of k equal to k times c, perfectly linear in k, okay? With a slope that is the velocity c, okay? This is the non-dispersive case, light in vacuum. Now, this is not certainly going to help in describing a non-relativistic electron traveling, okay? For a very simple reason. Electrons do not travel at the velocity of light, okay? And the momentum, I would like to have something for which the velocity with which something moves is essentially the momentum divided by the mass. You see, there is no mass, no momentum here. I mean, everything moves with the velocity of light, a common velocity. That's not non-relativistic quantum mechanics, non-relativistic motion. So I should look for something different for this object, okay? This cannot be just a linear function. Okay, let's see. I don't know the answer, and whenever I don't know the answer, I should try to derive it, okay? Let's see how. I don't know it, but I know that this is a function of k that in principle I should be able to expand. Expand where? Well, remember, this is a Gaussian that I am integrating. So there is an integrating decay with a Gaussian that centers everything into k0. And this is this function of k that I am looking at. Okay, well, suppose that this Gaussian is pretty narrow. So I'm integrating everything, some function, and then there is this Gaussian that makes everything quite narrowly peaked around k0. Well, then whatever this function has, as far as k is concerned, I can think that I will never go too far away from k equals 0. Okay? So my guess is that let's expand omega k close to this point. Okay? So this would be some omega k0 plus. Should I erase here? Yes, I need. Plus what? Well, the derivative at k0 times k minus k0 plus, well, the second derivative times k minus k0 plus, in principle, everything, but as always in this kind of calculation, you stop at the lowest reasonable level where you can perform a calculation, have all the necessary ingredients, but, I mean, you have to stop, okay? So this is a constant. I can treat it. This is a term in k minus k0. It's okay. K minus k0 is there. This is still k minus k0, and it's squared. And it's okay, because after all, this is still Gaussian-like. Okay? So I can keep exactly these three terms in the calculation without any problem. If I include k minus k0 cubed, I would be in trouble, because the integral would have exponential blah, blah, blah cubed, which is more difficult. Okay? So I stop there. The justification that the narrowness of G justifies just keeping only those terms. Okay? That's what we can do, and we do it. All right. Let me eliminate this, because I do have to make space. Okay. So let us do the calculation now with this expansion there. Okay? So once again, some patience. There is the c, there is the integral square root of 2 pi. There is the e to the minus alpha k minus k0 square from G. Then there is e to the I, let's see, k x. Why do I want to write it this way? No. Kx minus, okay, this is omega k0 plus, we call this object, formally is like a velocity. You see, it's a frequency divided by k. Remember, the velocity, the phase velocity v of k was omega k divided by k. Now is a derivative, however. Let me call it Vg. G stands for group. This is the group velocity as opposed to the phase velocity that I had introduced before. Okay? But just a name. And this quantity here, where is it? Okay? Let me just shorten it to beta. Some constant, beta. Okay, so this is T plus Vg k minus k0. There is a T always. Okay, let me put it everywhere. T plus beta k minus k0 square, and again T. Okay? So let us look. Yes, there will be. Okay.
Could you give us some?
It will come in 3 to 5 minutes, depending on the slowness that I have. Okay. It is related to the curvature. You see, I mean, if this was just linear, second derivative 0. So it has to do with the curvature of the dispersion omega k versus k. And you will see in a second that it's related to h bar and to the mass of the particle. Very short discussion will come. Okay, so let us see. Almost everything is now function of k minus k0, but there's a guy here. But I know how to make it a function of k minus k0, right? Remember the trick. Just put minus k0, x, and obviously you have to put e to the I k0 x out also. Okay? So I just introduce it. Well, once I have done this, well, first of all, let me change variables to k minus k0, which I should call k prime, but please allow me, just call it k. So the integral is c e to the I k0 x integral over a new variable k, which I keep calling k, e to the minus alpha k square, and then I have e to the I kx. Oh, what about this? Well, this is in fact not integrated at all. It's just a function. Okay, let me put it out then. Okay, make some space more. C e to the I k0x minus omega k0 t. Okay? So I get rid of this. Good. Then I have minus Vg k t. The t I put it here. Okay? And then I have minus beta, and I have t, and I have k squared. This is k minus k0, but it has become k. So let's see. First of all, here I have x minus vgt times k. Okay? So let me rewrite this. C e to the I k0x minus omega k0 t integral square root of 2 pi. Let's see, this piece is e to the I k multiplying x minus vgt, which is nice, right? It's just x shifted by this group velocity. This t square here, k square, sorry, goes with this k square. Same thing, except that I have to correctly account the fact that alpha appears here, and here I have minus I beta t. All right? Am I doing things correctly? I think so. So if I put the minus in front, is plus I beta t, and then I have a k. Okay? Square. Very good. So does this integral look in any way similar to what we have on the board? Well, yes. You see, it's essentially this integral. Now, you might object. In that integral, I was assuming a to be a real constant. At least a was real. Then the j there was imaginary, but a was real. And there was an important reason why a is real. For instance, if a is purely imaginary, then this thing is no longer a Gaussian dying, but something oscillating. And the integral maybe doesn't exist. But as long as this quantity a has a real part that is positive, not necessarily just real, but a real part that is positive. So think of this as a complex a belonging to the complex number, but where the real part of a is just positive. Would you be happy with that? Of course, yes, because the main thing, okay, the real part of a times k squared makes the thing very nicely going to 0. The imaginary part makes some oscillation, but the overall real part that comes, you can separate it in product of things. This makes things converging nicely, okay? So you can even enlarge your assumptions and say this formula is okay as long as a is even complex, but with a positive real part. And all of a sudden, this comes, in fact, complex, but the real part is alpha. See, this is a purely imaginary piece. Alpha is the same alpha there, so obviously positive, right? So alpha here, I always imagine alpha to be positive. So the real part is positive. No problem. So I can use the formula, okay? I'm now going to use it, and I have to, where did I put the, here. Okay. Now, so follow me. Here, I put, so there is this C, there is this e to the I k0x minus omega k0t. And then application of that formula, just remind you that here I have something and there I have a over 2, the usual dictionary. Read a over 2 in place of this and vice versa. And the result is e to the minus x squared. Well, not x really, this quantity square. So x minus vgt squared divided by 2a. Well, a should be reread from there. And believe me, it becomes 2 alpha plus I bt. Okay? This is A. Whenever you see A, you have to put 2 alpha plus I bt. Okay? Or 2 times 2, 4. Okay? And what about, well, there is this 1 over square root of A. So in the denominator here, I should put 1 over square root of A, which is 2 alpha plus I beta t. Okay? Well, obviously for t equals 0, you should recover the previous result. Okay? So if I put t equals 0 there, 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 check is exactly the previous formula. But now this is, well, much richer. For instance, it's telling you one thing. First of all, if you take the modulus square of it, so let us start looking at the modulus square. So the modulus square of psi x and t. Well, then this e to the I factor just gives you a 1. What about the modulus square of the rest? Well, c square is obvious. Here I have to be a little bit more careful. These are complex quantities, in particular a complex square root. So to take the modulus square, you have to multiply by the star of it and do the appropriate algebra without getting wrong things. Please verify, okay, that if you put the c that I've given you there, you will obtain the following thing. 1 over square root of 2 pi, square root of alpha divided by alpha square plus beta square t square. This alpha square plus beta square t square come when you multiply alpha plus I beta times the star of it, which is alpha minus I beta t. Okay? You take this, the product, you get alpha square plus beta square t square. Okay? Typical things. Then you have e to the minus alpha over 2x minus vg t square divided by, again, alpha square plus beta square t square. Okay? So please verify that the complex calculation is nothing but this. Okay? And now you see the point. First of all, this is a Gaussian which is centered around what? VGT. Okay? So the center of this Gaussian is moving, however, with the velocity that is not the phase velocity of any k, but the group velocity. So the object that matters is the derivative of omega k with respect to k at the important momentum k0. Okay? And this is what moves the center of the Gaussian. However, you see that whenever beta is different from 0, and notice the sign doesn't matter, because it's beta squared that always appears, at least in this modulus square, the width of this Gaussian increases. Okay? You see this is 1 over 2, the width square. The width is increasing. Okay? So not only the wave packet modulus square is moving, but is also broadening. Okay? And this is due to the fact that there is a beta different from 0, or if you want, there is a second derivative different from 0. Okay? Good. Now, so this is called spreading of a wave packet. The wave packet sooner or later will be just very, very, very broad if t becomes very, very large. Okay? You could play around a lot with this form. For instance, if you are knowledgeable about computers, you could try to draw these things as a function of time and see how the thing evolves in time, okay, and play a little bit around with this object. But what I want to point to you now is that we still have to determine how can we describe a non-relativistic particle. Now, you know that for a non-relativistic particle, the velocity should be equal to the momentum divided by the mass, right? And the momentum, according to de Broglie, was just equal to h bar, the k. But what is the important k here? You see, it's k0. The overall oscillation is with k0, okay? So I really want this. I want that the velocity with which this thing is moving is related to its k0 by h bar k0 divided by m. This velocity is the group velocity, by the way. Okay, the group velocity is the derivative of omega k with respect to k at k0. Can we solve this? So how should I take omega k in such a way that this derivative at k0 is just h bar k0? The square, right? Let's see. Omega k equal to h bar k square over 2m. Okay? If I take a derivative, I bring down the 2, and this cancels the 2, and I get, so the derivative of omega k with respect to k is just h bar k over m, and if I evaluate at k0, I get exactly what I want. Okay? So here is the solution. Omega k should not be the straight line you saw above. It should be this important h bar k square over 2m. Okay? A parabola. Okay? You see that the mass appears there, okay? And the h bar appears there. All right? What is beta? Well, let's see. Beta is equal to 1/2 a further derivative. So if the first derivative is this, okay, let's put a second derivative. I get another k off. So it's 1/2 h bar over m. Okay? So the parameter which gets for you the spreading of the wave packet is just h bar over m, apart from a factor 2. The higher the mass, obviously, the smaller is beta. In fact, a very, very large mass means a beta that is very, very, very small. In a second, I will try to get you some numbers to understand how really this thing can vary in a dramatic way if you consider small but classical things or electrons. Okay? For the time being, let me just pause for a second and ask if you are followed until now. Okay? So, unlike photons that have, in vacuum, a linear dispersion, electrons, non-relativistic electrons, to be described, you should take hk be a parabola. Okay? By the way, if I insist in, remember that AE was just h bar omega, okay? So if I call h bar omega k, I see that this is equal to h bar square, k square over 2m. And once again, if I use de Broglie, h bar k is the momentum, and so this is just the momentum square over 2m. Okay? Reasonable. The energy, which is h bar omega, is just p squared over 2m, the classical kinetic energy. Okay? Makes sense. Okay? So the message, in order to describe a wave packet of a non-relativistic particle, which should mimic something that classically behaves like the usual objects you know, you should take the dispersion omega k to be h bar k squared over twice the mass. Okay? So let's do this very simple exercise, numerical now. What do I erase? Here. Let me, before I erase that, how do I write the spread in x? Say the spread square in x at a certain time t. How do I read it from that? Remember, the rule is I should have e to the minus x squared divided by twice the spread. Okay? So I can read it directly, and is equal to what you have in the denominator, but obviously divided by alpha. Okay? So in other words, you write it like this, which is equivalent. Okay? This quantity here is the square of the spread at time t. At time 0, obviously, you have just alpha, the usual thing here. Okay? The previous result. Now, where is it? No, because I always take the factor 2 out in the definition of the width. Okay, the Gaussians always have the 1/2 explicitly out and then the width.
Yeah, but we say the uncertainty in k-space and the uncertainty in position space is 1/2.
Yeah, this was there, because in k you have a factor 1/2. Okay? But in x, there is no 1/2. Okay? All right. So this is the correct formula that I can read from there. And it reduces to this one when t is equal to 0. Notice this is the square. That is the square root of this. Okay? Okay, so I write this as alpha plus beta squared t squared over alpha. Or if I want delta x at times t, I take the square root and I get square root of alpha plus beta squared t squared of alpha. Okay? Just simple manipulations of the same expression. All right. Now, consider a Gaussian wave packet which is describing three possible things. The first thing that you might want to describe is an electron. Okay? So for an electron, the mass, how much is the mass? Roughly 9 × 10⁻31 kilograms. Okay? And suppose that the initial spreading, so the delta x at a certain time 0, was, I don't know, two possibilities. In possibility A, it is, for instance, 10⁻⁵ meters. And in possibility B, same mass, but the delta x, the initial spreading, is 10⁻⁻10 meters, 1 angstrom. Okay? Now we are atomic size. This is still, 10 microns, so pretty large on atomic scale. And then I have a possibility C that is a small but macroscopic object. So for instance, an object whose mass is 10⁻³ kilograms, a gram, okay? And the initial spreading of the wave packet is, for instance, well, it doesn't matter much. 10 to the minus 3 meters, a millimeter. Okay? So something of a gram and spreading on a millimeter. I would like to know what happens as time goes by now. Okay? So let us calculate.
Question.
Yeah.
Can you please repeat how you have concluded that is changing?
This one?
Yeah.
Okay. I read from this formula, okay, which I rewrote. The question was, how do I get this expression here, okay? So I start from this expression where there was an alpha here, which I put in the denominator there, okay? And now I say, whatever appears here, by definition, is the sigma x square, is the square of the width of the Gaussian, okay? And to give a slightly different name, I called it delta x square at times t. So this is just the sigma square x at time t, obviously, okay? So I just read it from that denominator. Alpha square plus beta square t square over alpha, okay? And then this is just a simple step. If I take the square root, because that's the square of the width, then I have a square root. Okay. So goal is to calculate the relative, oops, I erased one formula here, which was useful, 1/2 h bar over m. Okay, the second derivative of omega. Okay, now, let me proceed here. So I want to calculate the delta x at times t minus the delta x at time 0 divided by the delta x at time 0. The reason why I do that is because this is much simpler. I mean, it's the relative, you see, this is how much the width has increased with respect to the original one divided by the original one. So it's the relative increase, okay? Now, according to my formulas, I have this equal to square root of alpha plus beta square t square over alpha minus, at time 0, this is not there, so I have square root of alpha divided by square root of alpha. And then if I eliminate the alpha here, I get square root of, so 1 plus beta square t square over alpha square. Okay, I have divided this by square root of alpha minus 1. Okay? This is the relative increase. One warning. Whenever I was giving this exercise to do at home in the past years, what I was obtaining is the following. You start from here, and you immediately put all numbers inside, okay? Everywhere. As a result of that, this is full of 10 to the minus 31 squared and blah, blah, blah. And after a little bit of space, obviously, I mean, the powers of 10 were missed, and it was a mess after a very short time. So it was impossible to get to a result that, in the end, if you refrain from putting your constant immediately in the formulas, okay, please do it whenever is absolutely essential. The first thing you have to do is to do your algebra with less numbers than possible, okay? So just use alpha and beta and t and proceed. Once you are here, now there is nothing else but putting what is alpha, what is beta, what is, so h bar, m, you have to do it, okay? But before, no, there's no need. I can simplify alpha. And, okay, so let me just do it. The crucial thing for this relative increase is this factor here, okay? Beta square times t square alpha square. So let me concentrate on it. beta square is 1/4 h bar square over the mass square, and this is t square, and this is alpha square, so the initial spreading. So let me call it delta x0 square. Okay, so that's the important thing. I should compare this quantity to 1. Obviously, if this is very small, then square root of 1 plus something very small, I can expand and do. If this is large, then the square root is very different from 1, and I should calculate. Let's see. H bar in international units is 10 to the minus 34, okay? Appropriate action units. It would be 10 to the minus 27 in CGS, okay? Now, when I put, there is here some 1 point something, which I don't care. Okay, let's put it there. So I have 1/4 10 to the minus 68. I don't put the units, it's the action units, so whatever, energy times time, okay? So the units of h bar. Let me indicate like that. So, by the way, this whole quantity should be summed to 1, so it's dimensionless, no dimension. So the overall result is just a number. That's the reason why I don't even put the dimensions there. Okay, then there is a factor 4, then there is the mass, then there is the time square. There is the mass and the spreading. Okay, let's do first the case of electrons. Then this is 9 square, so 81. Then it is 10 to the minus 62. Obviously kilogram square. And then there is this delta x0 squared. So let's now the different cases are distinguished. Okay. So for instance, in the first case, I have here 10 to the minus 5 squared, which is 10 to the minus 10. Okay. So you see that here I have 68 and here I have 72. So for t reasonably small, this is small, but as t becomes of the order of, say, 10 or 100 or so, I mean, this starts to be considerably larger. Okay. You can calculate the exact thing when this, for instance, becomes 1. You can calculate when this becomes 1, for instance. Okay? You can do it. If the initial spreading is 10 to the minus 10, okay, it's even worse. This is 10 to the minus 20. Okay? So now this is large because, remember, this go up, because this is divided by a smaller quantity. So even for t of order 1, this is already large. So you should have, very, very small times. Okay? So you see that you have that this is of order 1 when t square is of order, let's see, forget about this numbers. Well, this is 10 to the 2, roughly. So this is 10 to the 10 to the minus 82, times 100, so 10 to the minus 80, say, something like this, divided by 10 to the minus 68, okay? So 10 to the minus 12, okay? So of order t, 10 to the minus 6. Whenever time of order 10 to the minus 6 seconds, already this term is as big as the original one, okay? Okay, what about the microscopic but classical object? Well, I have now, I erase here. rather than 10 to the minus 62, I have 10 to the minus 6 kilograms square. And here I have 10 to the minus 3 meters, so 10 to the minus 6 again meters square. So you see I have 6 and 6, 12, okay? And this is 10 to the minus 68, okay? So the overall thing is 10 to the minus 54 or whatever, 56, okay? And obviously I need the time of the order of 10 to the 27 in order for this to be 1, which is astronomically large, 10 to the 27 seconds, okay? I mean, you can calculate how many seconds there are in a year, in a century, okay, in a millennium, and this is much larger than that, okay? So you see how a mass of order a gram, which is small, is so much larger than the mass of the electron, and especially for the fact that there are squares here, the spreading of a classical-like object is totally useless. I mean, you can forget about it, but if you are in the atomic world, in the world of electrons, where the masses are so small, then the fact that h bar is so small is very important, okay? And you can, I mean, the fact that h bar is small, but not infinitely small. I mean, if h bar was essentially 0, then no quantum effects, you see, okay? Because this would be just 0. Huh? But no, this is not 0, and the small mass makes the result exploding with time very fast. Okay? Is this clear to everybody? Okay? So the role of the mass and of h bar in this spreading hopefully was clear from this exercise. Okay, so I would end the lecture here. Next time we start with the Schrodinger equation. This was not a proof of the Schrodinger equation, but we are essentially at the verge of introducing the Schrodinger equation in a way that is more understandable than just writing it. Okay? In some sense, we can immediately show, and we'll do it next time, that this wave packet that I have written here, this one, okay, when omega k is equal to h bar k square over 2m, as I have insisted, then this object here solves the following equation. The derivative with respect to time of psi x and t is equal to minus h bar square over 2m, the second derivative with respect to x of psi x and t, okay? Which is the Schrodinger equation for a particle in vacuum, so no potential. We'll show this next time. And in fact, this is the most general solution of this equation. So it's a superposition of plane waves with an arbitrary g of k, by the way, not necessarily Gaussian. The specific calculation we have done for Gaussian was because we could do the algebra, I mean, till the end. But in principle, any g of k is allowed and is a solution of this. Okay? We'll do next time. So if there are questions, otherwise we see.
Here we go till the second order correction, right? When we expand, we go till the second order correction.
Right.
If we go beyond, like if we consider the third order correction, then what kind of information can be expected?
Okay. The question was, we stopped in our expansion of omega k to second order. What would be the result if we proceed to third order? Well, and more. First of all, it happens to be that the correct non-relativistic limit is exactly quadratic in k. So the third order is exactly 0. This would be a semi-answer because, after all, life is not completely non-relativistic. The dispersion of particles, as Einstein has explain to us would be that the energy is the square root of p squared c squared plus m squared c to the fourth. Okay? I'm sure you have seen this at least in this form. Okay? If you put the momentum equal to 0, so the rest energy of a particle of mass m is E_mc squared. Okay? It's many T-shirts about Einstein. Okay? Okay. So this is the energy associated to the mass. And then there is this p squared term in this form. Now, you might ask, where do I get this p squared over 2m from? Look, usually this is very large. Okay? For electrons, mc squared is mega electron volts, very large energies, which are not very important, however, unless you break electrons, you produce electrons, unless you do high energy scattering of electrons, where this energy can be released. Okay? For condensed matter, electrons are never broken, okay, or never paired with positrons, or never disappearing. They are there all the time, and they move at relatively low speed, okay? And therefore, you never involve this rest energy as an important energy in your thing. So let's do the exercise. Just put mc squared in front, okay? So this is 1 plus p squared c squared divided by m squared c to the fourth, right? Okay? It's the same thing that I have written. C squared. Okay? So this is like that. Now let me expand for small p. So this is equal to mc squared. The expansion of the square root is 1 plus 1/2 p squared over m squared c squared plus a term of order the square of this. So p squared over mc squared c squared squared. 1/8. I think there is a 1/8 factor, but it doesn't matter. Now, look, this piece is exactly the T-shirt, mc squared. Now, what about this? mc squared, the c squared and the c squared cancels here, and the m cancels the m squared and becomes p squared over 2m. Okay? C disappears because this is non-relativistic, and you see you have the nice expression. Okay, so this object starts from the rest energy, mc squared, and then it has the parabola that I drew before. If you insist and you go to very, very large momenta, will not go forever quadratic. Sooner or later you will see that it straightens. Okay, after all, when this is much larger than this, it becomes again p times c, like the photon. So at that limit, it would make sense to ask again your question. The quadratic term, it doesn't live forever, but at this point, non-relativistic quantum mechanics breaks down in some sense, and I should do a full relativistic Dirac theory of quantum mechanics, which is not what we are going to do in any case. Okay? So the spreading of a wave packet in relativistic quantum mechanics is another calculation. Okay? You have to account for this in full detail, not just the third order term, and it's a complete.
Not the derivation, but what
No.
is? Okay.
No. It's a completely different thing, and to be honest, I mean, I haven't looked at it in the last 15 or 20 years, maybe, so I would not adventure in discussing the physics of it. Okay? Other questions? If not, so we see each other tomorrow again. Okay? Bye-bye.